Thank you to everybody joining us today. I'm excited to talk about best practices for measuring sulfur using monochromatic WDXRF. Sort of a little history to kick things off. So sulfur limits in gasoline. Tier 1 started back in 2004, putting the limits at 120 ppm. Pretty quickly then moving on to Tier 2, which was at a 30 ppm limit. Now, over a decade later, once again, those limits are moving lower. So the sulfur in gasoline requirements will drop to 10 ppm next year. There are about 30 small refineries that can wait until 2020. So beyond the Tier 3 requirements, which are adding a PBMS or performance-based measurement system requirement to the statistical quality control that was implemented with Tier 2, there's now a regulated way that you need to monitor your data quality importance. But there's reason to want the best possible data beyond that. Sulfur removal costs refineries millions of dollars per year. That's partly capital. So as these limits are moving lower, many refiners are having to invest in new equipment to remove more sulfur from their different process streams. The process itself requires hydrogen to make it work. You can see here a bit of a diagram of one of these desulfurization processes. The process uses a catalyst, and this has a fixed life. So the more heat, the more sulfur, the harder you're running that catalyst, the faster it's going to be used up. And so limiting that wear down on the catalyst is definitely of importance. It takes energy to remove sulfur, and as we're talking about gasoline, it has an effect on octane. So as you improve your data quality, this is going to reduce the variability in your sulfur measurement. So if you reduce the variability due to the measurement, this means that you can be controlling your processes and controlling your finished product closer to that 10 ppm specification. And because of all of these things I mentioned, ultimately, you're going to end up reducing the overall removal costs. Just a little bit more about loss of octane. So in particular, the post-treatment at the FCC can convert many of the olefins from that stream. And those olefins actually are a contributor to octane. So I've actually spoken to people this year, specifically dealing with this issue as they're moving from 30 ppm to 10 ppm. How are they going to make up for this octane loss? This typically is often made up by reformate, and so there's limitations to that. And so as much as possible as you can be moving closer to that 10 ppm limit, the impact on the cost is going to be pretty significant. How can you reduce and how can you better control your processes? So in addition to having the simplest and most precise measurement in the laboratory, you can also be doing this in an online process. So XOS also has an MWDXR system that can be put throughout the refinery and be controlling the processes better at the different locations where desulfurization is taking place. I wanted to cover the technology being used in this really quickly. So XRF, X-ray-based sulfur detection, is very popular within many places as a technique that's been long used for measuring sulfur in gasoline, diesel, and other hydrocarbons. A typical system would be a wavelength dispersive X-ray fluorescence system. You can see a schematic here. It starts on the left, this red box. This is the X-ray tube. So this is the source of the energy that's going to create the sulfur detection. Typical X-ray tube is going to create X-rays at many different energies. You can see in the lower left, there's a schematic of what this energy looks like. So if often sort of a metaphor you can use is an X-ray tube has many energies, the way white light from the sun has many energies. And as you pass it through a crystal, you can separate out those energies and actually see a rainbow. Similar thing happens with an X-ray tube here. So you can see, though, that there's a peak in the energies at a selected wavelength for these X-rays. Now, this peak is determined by the metal anode that's used inside the X-ray tube. And what you want to do when you're setting up an XRF system is you want to select a peak energy that's above the energy it's going to take to create a sulfur signature, but not too far above it, because the closer you are to that energy, the better the X-ray fluorescence signal you're going to create. So this energy from the X-ray tube is directed at the sample, so gasoline is what we're talking about here today. This is going to knock out core electrons using the X-ray energy, and as those electrons are knocked out, electrons from the further shell electrons are going to fall in and replace that core electron. Now, as it does this, it's going to reduce its energy, and it's going to kick out a fluorescent photon. Now, this is what's represented by the green, essentially X-rays that you see here. Down in the bottom right, you can see now the graph of what this energy looks like. So there's peaks at the different elements that are of interest. So here's a sulfur peak, here's a chlorine peak. But you can see, because there's all of this energy that is not being used to create the fluorescence, these peaks are elevated above the base energy. So there's a background there. And that comes from these other energies besides the peak or the energy being used to create the fluorescence. This energy is typically passed through a filter, which will lower the overall energy, so it'll lower the peaks and the background, but it won't eliminate the background. So this, you can then see this is directed at a flat crystal. What happens at this point is a diffraction. So all of this different energies, besides the one at the sulfur, will not be redirected towards the counter or the detector at the lower right. So it'll select, and this is what's shown in the top right by the red boxes, it'll select just the wavelengths that are for the element of interest. So there's a sulfur or there's a chlorine. In this case, we're talking about sulfur. So at this point, the flat crystal often will then also be rotated so that it's oriented to look at a background level. So you'll take the peak sulfur energy and you'll subtract the background from it. And this is how a typical wavelength dispersive XRF works. So the intensity of these peaks after it's been corrected for the background is correlated to a calibration curve. So you'll run a 0, 1 ppm up to an upper bound, and you'll bracket the concentrations that you're interested in. So 10 ppm would be the level that we're talking about today. And you can create a linear curve based on those intensities and correlate it to a known concentration. XOS uses what's called monochromatic wavelength dispersive XRF. So it's fundamentally the same type of technology, but it takes it a step further. In this setup, you can see there's the same X-ray tube. The top left chart should look pretty similar. This is directed at a doubly curved crystal optic. So rather than being a flat crystal that we saw in the traditional WDXRF, this is curved in two directions, if you think maybe like a spoon or something of that shape. Now, at each point along this doubly curved crystal, it has the correct angle to select the peak energy from the X-ray tube. And so what it does is it filters out all of the other energy that's not used for creating the fluorescent signature, and it eliminates those. And because it's doubly curved, it also focuses that X-ray excitation. Because of this, we're able to create a benchtop analyzer rather than a much larger analyzer that uses a much higher energy X-ray tube. So a lower energy X-ray tube is then focused onto the sample, so the gasoline in this case. You can see the second. So after it goes off the doubly curved crystal, it's very intense, but it has eliminated or filtered out all of the other X-rays that are not useful for creating the fluorescence. Then after it goes to the sample, the fluorescent signature is again created, but you can see here in the third graph at the top that the background is much, much lower. And once again, the angle is selected just for that sulfur peak. And just those are directed to a detector. The same kind of calibration is done, but you can see here the background's been eliminated, and so there's no need to do a background correction at this point. This is a nice feature for the instrument because it creates a measurement system that takes about half the time and has better performance because of the doubly curved crystal optics. Here is our line of SINDI sulfur analyzers. We have analyzers that comply with ASTM D7039. That's a monochromatic wavelength dispersive method, as well as ISO 20884. The ISO 20884 method has versions for both the polychromatic, that would be the traditional WDXRF, and a specific part of the method set up just for monochromatic wavelength dispersive XRF that we're talking about here today. We have versions that go as low as 150 parts per million for a limited detection. You can also see a comparison at 10 ppm of the different repeatability and reproducibility for these methods. I'll get into a little bit more detail what that means. We also have a line of SIND 2622 analyzers. These comply both with ASTM D2622 as well as D7039. So because it's a subset of WDXRF, we're able to use the monochromatic excitation and still comply with the traditional WDXRF method. This gives a lot of flexibility to the end user. Because D2622 is an older method, oftentimes it's in more product specifications. It may be in requested by commercial partners, and it enables you that flexibility to have the precision of monochromatic wavelength dispersive and still meet the 2622 method that you may be looking to comply with. We also have a portable analyzer. That's the SIND OTG you can see over to the right. This is great for applications where you may want to get outside of the lab, perhaps mobile van type of applications. So we're talking about data quality in this presentation. I wanted to just touch on a couple of precision definitions from ASTM. The main point being reproducibility. This is the between lab difference. So this is the same method by different laboratories using a different apparatus on an identical test material. So this is the difference, the maximum difference you would expect only once in 20 samples to exceed. So about 95% of the time you would expect, based on a reproducibility number, that you would get within that difference, the two samples. Repeatability, this is within lab difference. So this is the same user on the same apparatus on the same material repeating the measurement in a short interval of time. So in that case, once again, this is a 95% confidence, or a 1 in 20, you would expect a larger difference than that. Really, what we like to focus on is reproducibility, the between lab difference, because that's what's going to come into play when you're certifying a product, and you want to know that in a commercial transaction that when they test it on the other end, that it's not going to have a difference. It's not going to be out of specification, or if you have a regulator that's checking against that you're meeting the Tier 3 requirements, that they're going to find a difference. And because you have that reproducibility number that is as low as possible, you can be as close to the specification as possible and reduce that overall variation in the sulfur measurement. You can see some different sulfur test method reproducibility. These are from the ASTM test methods. So at the top, we have an EDXRF method. I didn't cover that, but it's not typically used for Tier 3. So because of the precision and the limits of detection, the method doesn't cover the range going down below 10 ppm. We have D5453. This is a UVF-based technique. And you can see here that has the second highest reproducibility, and then the two technologies that we talked about here. So the WDXRF, the D2622 method, and the MWDXRF method, the D7039 method here. So across a wide range of concentrations and even down to the low range at 10 ppm, MWDXRF has the lowest reproducibility. So this data was generated at in a round robin that was done when the methods were done, and so on a limited basis with controlled samples that were sent out. I also wanted to talk about another way that we can show reproducibility is there's an ASTM interlaboratory cross-check program for reformulated gasoline, 1 liter sent out to participants of the study. So these are hundreds of real-world end users that are checking their performance, and they test a number of parameters, but the one I wanted to talk about was, of course, sulfur. And so people who participate are either doing D2622, the WDXRF method, D5453, the UVF method, or D7039, the MWDXRF method. So this chart, there's quite a bit in here, so I'll do my best to explain this. You can see red dots on the chart. These correlate with the right axis as you're looking at the screen. So this was the mean sample concentration for that month. This shows the data that was collected by the Interlaboratory Crosscheck Program from January 2015 through June 2016. For each month, you can see the reproducibility for each sample that was collected. On the bars, this correlates with the left axis. So the orange bar for each month is D7039's reproducibility. The green bar is the WDXRF method, that's D2622. And the blue bar is UVF, the D5453 method. So over this pretty long period of time, you can see, and across a variety of sample concentrations, you can see that MWDXRF has, on average, the best reproducibility for sulfur and gasoline. So if you're looking to reduce the costs and to meet the requirements for the Tier 3 PBMS and SQC, as well as reduce the costs of sulfur removal, we would really recommend that you use D7039 because of the reproducibility advantage that it has. So just real quickly before I get into the best practices on how you achieve this performance, just kind of recap. So Tier 3 measurement requirements, so the PBMS requirements and the SQC requirements actually went into effect back in January of 2016. But the actual requirements for the average sulfur level per calendar year doesn't happen for, till calendar year 2017. And so because of this, many labs that are out there preparing for this may not actually be seeing 10 ppm sulfur levels on a regular basis. So it's a great time to freshen up on the best practices before you start seeing those samples much more frequently. Because we found that little things, very simple things to take care of can have a much bigger impact on your data quality than they would when you were measuring 30 ppm even. So as I go through the best practices, I'm going to start with some good laboratory practices, just things in general that are good to do. Go through sort of daily activities, and then cover sample preparation to make sure that we all are on the same page about the best way to prepare samples to get the best data quality. So it may not be a surprise for most people that work in a laboratory on a regular basis, but cleanliness is really key. The sample preparation where you're working, keeping that clean, if possible, using a vented hood can be beneficial, and storing materials in sealed containers that are in a dust-free area. So you can see here cleanliness, we're talking about dust, and this will sort of be a repeating occurrence. You'll see that dust can actually be one of the biggest things that can have an impact on your data quality when doing this. Don't reuse. So it can seem easy to do, but reusing sample cups or pipettes are really going to have a big impact on your data quality. And while it can seem like a good way to save a little money, when you're thinking about the impact to the larger refinery, it's going to have a much bigger impact not having the absolute best data quality that you can achieve. And so making sure not to reuse is one of the simplest and easiest ways you can do to make sure that you're getting the best quality data. When you're preparing your samples, it's best not to queue up a lot of samples. What you want to do is start preparing your sample, if you're doing several in a row, towards the end of your last measurement, so that you can measure your sample as soon as possible after you've prepared it. The sample chamber of the instrument. So you want to keep this area clean to avoid contamination. So daily really goes a long way. You want to use a reagent-grade IPA on isopropyl alcohol. You want to clean the sample basket, which I'll go into more detail about. You want to clean the primary window, and you want to clean the sample weight. So in the picture here, you can see sort of the two silver discs with the black plastic piece in the center, sort of in the top right. That's actually the sample weight, and what that does is it holds the sample to a consistent height so that you are able to get the reproducible results. But what can happen is you can get sample on that weight, and it can cause contamination. So you want to make sure that you're daily cleaning that, and if you do see that it has become dirty, you want to make sure that you clean it at that time. Once again, the secondary window, it's another thing that you want to change daily. In addition to changing the secondary window daily, if you're changing the concentration, so If you're going from measuring a process stream or a crude oil and then switching to measuring a Tier 3 gasoline sample, if the sample's previous concentration was above 50 ppm and then you're moving down to 15 ppm for a diesel sample or 10 ppm for a gasoline sample, at that point it's a good idea to go ahead and change your secondary window film to make sure that you're getting the best result that you can, because that can actually cause contamination. So I mentioned that I would talk more about cleaning the primary window. If you're looking to get the best quality data, we'd recommend that you clean it daily. This is a stainless steel disc that sits under the sample basket. There's a thin Kapton film that's actually where the X-rays pass through to interact with the sample and take the measurement. Fortunately, it's very easy to do and fast to do to clean this. What you do is remove the sample basket. You want to soak a foam-tipped swab in reagent-grade IPA. You want to shake off any excess, so you don't want a lot of extra IPA on the sample primary window. You want to gently clean it, keeping the swab parallel. What we found is to prevent puncturing that thin Kapton film, what you want to do is not poke down on it. You want to keep any hard or sharp objects away from it, and just use the swab and swab it very gently, avoiding excess force. Once you've done that, you can go ahead and dry the window using canned air. You want to monitor, so you don't want to invert the canned air or shake it before using, because you might get propellant come out. If you do observe propellant coming out of the canned air, just go ahead and repeat the cleaning procedure, and you should be fine. Okay, next is the sample basket. So this is the part that sits on top of the primary window. It acts as another layer of protection from both contamination of the instrument and prevents spills from getting into the analyzer. If you do have a spill, it's very easy to remove this and change it quickly. But you also want to change it if you're looking for the best quality data on a daily basis. And so after you remove the basket, once again, you want to wipe it down with IPA. Use canned air to dry the basket. Next, we're gonna put the film in place. So you want to take a thin sample, so the same film that you would be using for your sample measurement, and you want to spray both sides off with canned air. With the basket upside down, so usually placed on a hard surface, you want to place the film on the sample basket. There's then a small plastic capture ring that sits on top of the film. You want to really avoid touching the film with your fingers, because even though it may seem surprising, fingerprints can actually affect the measurements in the same way that dust do, causing you to have added variability in your measurement. So then using 4 fingers is what we found to be the best. Just press firmly on the ring until it's set into place. This should capture the secondary window in place. You then want to observe it and make sure that it's not wrinkled. If you do observe wrinkles, just go ahead and remove that one and repeat the process. After you've placed the secondary window back into place on top of, or the sample basket back into place over the primary window, you should be ready to measure. Moving on to just some tips for sample preparation. You want to thoroughly swirl the sample bottle before removing a sample to ensure homogeneity. So you want to make sure that there's no variability happening from any settling or separation that's happening in the sample. When you take the sample cup, you want to go ahead and use a canned air to blow any dust particles out of the inside of the sample cup. What can happen is after you've prepared the sample and turn it over, that dust can move down to the film and create scattering that will add some variability to your measurement. Using a new manual disposable transfer pipette, go ahead and put the sample into the cup. Sort of the rule of thumb is to fill it the cup about halfway. It's typically about 3 pipettes worth of sample, particularly for a gasoline. Sometimes with heavier or thicker samples, that volume can be a little bit different, but you just want to go ahead and fill it about halfway. So then we're going to assemble the sample cup. Once again, you want to gently blow off any dust particles from a new sample film using canned air, and making sure that you're not getting any propellant on the film. If you do get any propellant, just go ahead and use a new film. Always use the same film type, just real quickly, as you use for your instrument calibration. So the different films can have a little bit different absorbances, different scattering. than each other, and so you want to make sure that you're using the same film type as you use for calibration. If you do choose to use a different film, it would be a good time to go ahead and recalibrate using that film. So after you have a clean film, you want to go ahead and place it over the half-filled sample cup, as you can see here in the lower part of the screen. You then want to install the collar of the sample cup. So you can feel the collar has a half-round edge on one side. This is the bottom. You want to place this down towards the film. Once that's in place, you want to go ahead and press down firmly. 4 fingers, once again, works pretty well. And you also want to, once again, make sure that you're not touching the sample film with your fingers. Any residue or fingerprints on the film can actually affect the measurement. Once you've assembled the sample cup, you want to check the sample film. So once again, you want to make sure there's no wrinkles or swelling apparent. You want to make sure that the sample cup is not leaking, even if shaken. If you do have that, you want to go ahead and start over. You want to go ahead and get a new sample cup and repeat the procedure. If you do have a good sample cup, a good sample prepared, you want to go ahead and use canned air to blow any dust off the film, and then turn the sample cup over and place it on a stand. And the stand will keep the film from getting any contaminants on it, and that could affect your measurement. At this point, you want to make sure that you vent the sample. You either want to use a new push pin for each sample so that you're not contaminating the next sample, particularly if you're switching between different concentrations or different sample types. Or you can go ahead and clean the same push pin, maybe using a Kim wipe with some IPA on it. We do recommend always using 2 vent holes and doing it across all sample types. By providing that venting, if you think of gasoline, it's going to build up pressure, and the film is actually going to bow out a little bit. That'll change the distance between the X-rays and the sample cup, and it will cause you to have your results a little bit skewed. If you go ahead and vent all sample types, you have no risk of that happening. One thing that we've noticed that happens is the bottom of these sample cups, they do have a little circle in the middle. And this sort of, just naturally to people, seems like a bullseye. This little ring is actually the bottom of sort of a height indicator. So as you're filling the sample cup, there's a plastic piece in the middle that can also serve as a guide to show you about half full. But if you vent it at this hole, you actually may not get venting because that plastic piece may go down and into the liquid and not provide actual venting. So you want to avoid venting your sample in the center and go ahead and put those 2 vent holes somewhere in the middle to the edge. Once again, just a repeat. So you want to analyze your sample as soon as possible. So as you can see there, it's really simple things that's going to make sure that you get the best quality results. Always good to just have a brush up on those kinds of things. So moving back to the PBMS testing. So as part of PBMS, there's 3 parts of it. There's 2 accuracy pieces and 1 precision piece. So the first part of the accuracy testing is you want to take the arithmetic average of 10 continuous tests of a commercially available gravimetric sulfur standard. This needs to be in the range of 1 to 10 ppm. Their example here is for 10 ppm. The standard shouldn't differ by more than 0.70 parts per million. So we did do the testing here at XOS in our applications lab. You can see here we used a 9.0 ppm commercially available gravimetric sulfur standard in gasoline. You can see that the average was 9.43 with a standard deviation of 0.22 with a percent RSD of 2.32%. That 9.43 average was 0.43 different than 9.0, and so this is less than the 0.70 ppm sulfur required by the PBMS accuracy testing, and so that would be a pass. The second part of the accuracy testing is repeating a similar test on a commercially available gravimetric sulfur standard in the range of 10 to 20 ppm, and the maximum difference between the average reference value and the mean needs to be less than 1.02 parts per million. So you can see here we completed that testing using a 19.0 ppm commercially available gravimetric standard with an average of 19.33 with a standard deviation of 0.32 and a percent RSD of 1.64. The 19.33 average is 0.33 different than the average reference value, and that's less than the 1.02 ppm sulfur requirement for this section of the PBMS accuracy testing. The last section of the PBMS is a precision test. So this is a test of the allowable standard deviation for at least 20 tests made over a minimum of 20 days. You're allowed to batch these in groups of 4, so you need to do a minimum of 5 batches of 4 tests, 4 or fewer tests, with only 1 batch allowed per day, and once again, at least over 20 days. The standard deviation of those minimum 20 tests must be less than or equal to 1.5 times the repeatability divided by 2.77, where R is equal to the ASTM repeatability of ASTM method D7039. They do give you an example here where they calculate the maximum standard deviation of 0.94 for a 10 ppm sulfur gasoline sample. So once again, we did do this testing. So over a series of 20 days, we did 36 samples, so more than the minimum requirement of 20 samples over the 20 days. We did do batches of 4 per day that we did testing. You can see across these 36 measurements that the standard deviation was 0.36. Using the average value of those tests, we calculated the maximum standard deviation of 0.99. So you can see this is much less than the requirement, and so that would be a pass for the Tier 3 PBMS precision requirements. The Tier 3 standards also require you to follow D6299 precision, statistical quality control. The data you saw in the previous graph, we went ahead and put into the eye charts, the histograms, and the MR2 charts. You can put together your own charts following the procedures in D6299, or there's also a lot of commercially available software that can set up these charts for you. So that's the information I had on the best practices for using 7039 to meet Tier 3 requirements for PBMS and SQC. I did want to mention that MWDXR is also available in online, and so you can get those data quality benefits as you're looking to optimize the performance and the processes that are impacted by sulfur that can be a part of meeting the Tier 3 requirements at the end. Some of the benefits of using online MWDXR is that it's a direct measurement technique. So there's no combustion gases or high temperature furnaces in your process. They're extremely low maintenance. The typical maintenance interval is 3 to 6 months. And so that really means that you can be collecting that process data and optimizing your process and not having to touch the analyzer for very long periods of time. What we find is the more often an analyzer needs to be touched, the more likely it is to have variation, the more likely it is to get neglected. And once an analyzer is not giving you good results, it's not really of that much value in the process optimization that you're trying to do. Some applications, it's very valuable to have rapid instrument response. Using MWDXR, you're able to register changes in seconds rather than minutes with some other technologies. In addition to sulfur, there's some application where chlorine is valuable, and we also have online chlorine measurement available. One of the benefits as well is that you have the same technology used for both lab and online measurement, and so you can expect that you're not going to have any differences result because of a change in technology between what you're using in your lab and what you're using in the process. I mentioned rapid instrument response. Here was some data generated by a customer of ours who was using MWDXR online in some blending operations. They were able to make precise fuel interface cuts for transmix as well. So this one you can see there was a ULSD sample passing through a pipeline. They were switching to jet fuel, and so they were able to determine when to make that cut and to reduce the transmix that they were generating. So you can see within 60 seconds, the instrument was fully normalized to the new concentration of the jet fuel, but within 30 seconds, you saw a very significant response, and even in the 10-second range, you could start to see that. And so in blending and transmix applications, it can be very valuable. Here's some data generated at a major North American refinery using online chlorine detection. You can see they were looking at sub-ppm levels of chlorine. What we're hearing from customers is, corrosion's becoming a major concern for refiners. It can be billions of dollars a year for the industry that they're losing to corrosion, and chlorine can be one of the big culprits. So you can monitor the performance looking for upsets in your desalter. You can see if perhaps you're getting a crude source with maybe a slug of undesaltable chlorine or organic chlorides that won't be desalted. Once again, just to wrap it up, we were just talking about the Tier 3 maximum average sulfur level isn't going into effect until calendar year 2017, which is going to be here very soon. And so it's a great time to recap these best practices because you may not be seeing samples that are down to that level yet. And, the effects of even small things can be larger at these lower concentrations. And so brushing up on these things is really valuable. We talked about how monochromatic WDXRF provides the most reproducible sulfur measurement in gasoline. And so you can have the confidence that you're going to meet the Tier 3 requirements as well as minimizing the safety factor that you need away from that 10 ppm to meet the requirements and lower the costs that actually are associated with sulfur removal. Just a few simple best practices will really ensure that you have the optimal data quality in your lab. So I wanted to thank everybody for joining. If you have any questions, I'm happy to answer them. You can see my contact information, and we appreciate your time.
All right, Kyle, looks like there are no questions coming in.
All right. Well, once again, I wanted to thank everybody for their time. If you do have any questions, you can get in touch with myself, and I'd be happy to answer. Copies or recordings of this will be available in the future if there's anybody you'd like to share them with, and we'll go ahead and send those out to the participants. Thank you very much for your time.